Hello everyone. Today we are gonna see about quantum sensors and how it is different from the conventional sensors, the different types of quantum sensors like quantum gravimeters, quantum magnetometers, Hall effect sensors, and other four types of sensors, and the application of these sensors and the working principle. So, what do you know about quantum sensors and on what basis they work? Like, can anyone of them answer this question? Yeah. Let's see an overview of what quantum sensors. Look, generally, quantum is a discrete amount of energy or a small amount of energy or package of energy proportional in magnitude to the frequency of the radiation it represents. It's like using quantum sensors. It's a groundbreaking approach to sensing, and it has a unique properties of quantum mechanics to achieve unprecedented levels of sensitivity, precision, and accuracy. In this lecture, we'll explore the principles of quantum sensing, underlying quantum phenomena, and the diverse applications of quantum sensors across various fields. First, let's see the evolution of quantum sensor. In the early 1980s, discovery of the quantum Hall effect sensor was discovered at 1980. This was done by Klaus Kornblad breakthrough in quantized conductance in two-dimensional electron systems under strong magnetic fields and low temperatures. And in the early 20th century, there was a great work in quantum mechanics. Uh, Atomic magnetometers were developed because of to study the atomic behavior and magnetic field interactions. Development of atomic magnetometers was done by scientists like Ramsey and William Harper. This is a general overview of evolution of quantum sensing. And next, what is quantum? It refers to the fundamental principles and fundamental quantum mechanics. It's a branch of physics that describes the behavior of particles at the atomic and subatomic levels. And it was developed in the early 20th century. These concepts were introduced apart from the classical physics. And let's see the key concepts of quantum mechanics. The four key topics are wave particle duality, superposition, entanglement, quantum tunneling. Like how the importance of sensors is for mechatronics is the importance of these four concepts for quantum mechanics. So let's see one by one how what is wave particle duality, what is superposition, and these four topics in one by one. And next we'll see its working principle, operation, and everything. What is quantum entanglement? It's a phenomena where the quantum states of two or more particles become correlated regardless of the distance between them. Let's say there is a particle A and there is a particle B. So there are two particles or atoms or subatoms or two or more particles. It is in a distance of more than 1 meter. Now, the quantum entanglement says it's a phenomena where the quantum states of A and the quantum states of B become correlated. That is A and B. This is called as quantum entanglement. These entangled particles exhibit instantaneous correlations. That is, they exhibit correlations very fastly and very instantaneously, allowing for synchronized measurements across vast distances. That is, even for longer distances than 1 meter. Quantum entanglement enables the development of quantum sensors with enhanced sensitivity precision, particularly in distributed sensing applications. So, what are distributed sensing applications in quantum sensing? Using quantum entanglement, we are gonna do this. Let's see how we are gonna do this. Let's say you have a particle. So, using quantum entanglement, how distributed sensing applications are done. So, what is distributed sensing? It's a technology that enables continuous real-time measurements along the entire length of fiber optic cable. Let's say for a fiber optic cable, the entire length is always in a feedback mechanism where it is sensed and it is continuously monitored. Unlike the traditional sensors that rely on the discrete sensors measuring the predetermined points, like it is not uh, measuring or sensing at only the predetermined points. It always senses in a continuous manner throughout the length of the fiber optic cable. This is called as quantum entanglement. And the next property is superposition and interference. What is superposition? It is a fundamental principle of quantum mechanics. It is one of the fundamental principles of quantum mechanics that multiple states, it can exist in multiple states simultaneously. Most quantum sensors depends on superposition to enhance sensitivity and resolution. So it is an important property of the quantum sensors. Let's say you have two signals. One is A, signal A, and another one is signal B. So using the superposition principle, the output of A plus B, which is equivalent to A plus B, this is called a superposition principle, which produces a high sensitivity and resolution. That is, a good output is given by the quantum sensors using the superposition principle. Like, which is similar to the superposition, we have another phenomenon called as interference. The quantum inference and Ramsey inference enable precise measurements by exploiting the constructive and destructive interference of quantum states. You know what is constructive and destructive inference of quantum states, which is similar to the superposition principle. The next slide, we are gonna see about wave particle duality. What is wave particle duality? This is a phenomenon exhibited by the quantum mechanics. The particles such as electrons and photons exhibit both wave-like and particle-like behavior. So wave is something like the sound waves or the light waves, while the particle-like properties is something atoms. The both properties are exhibited by the quantum waves. This duality is a fundamental aspect of quantum mechanics, and the key aspects of wave-particle duality are wave-like, particle. The quantum sensors or the quantum mechanics basic principle and the key aspects are it wave-like, particle-like, and uncertainty principle. What is uncertainty principle? It's bit different. Uncertainty principle is how much error the atoms or the subatoms produces in its own state. It's called as uncertainty principle. So these are the basic principles of quantum sensing. And in the next slide, we are going to see about the principles of quantum sensing. Quantum sensors exploit quantum phenomena to measure physical quantity with unprecedented precision. It has a high precision and high sensitivity and resolution. Unlike classical sensors, which rely on macroscopic properties, quantum sensors leverage the inherent quantum nature of particles to achieve high sensitivity and accuracy. In classical sensors, let's say the precision or the accuracy of the sensor is around 0.1 percentage or 1 percentage. In quantum sensors, which is 1,000 times much better than the classical sensors, that is 0.0001 percentage. So that how the quantum sensors work and how what is the principle of quantum sensing, we are gonna see in the next slides. Using quantum phenomena, these quantum sensors work, which depends on superposition, inherence, coherence and interference, destructive interference, quantum entanglement, and wave particle duality. So using these principles, quantum sensors work based on these principles. Quantum sensors detect very small changes in the environment, such as the magnetic fields, gravitational waves, and electromagnetic radiation with remarkable precision. That is, remarkable precision is very, very, very high precision. These changes are noted by the quantum sensors. So, in the next slide, we are going to talk about the difference between conventional sensors and quantum sensors. So, what is the difference between conventional sensors and quantum sensors in the basis of principle or the phenomena? So, the conventional sensors operate based on the classical physics principles such as the electromagnetic induction, the piezoelectricity, or the thermal conductivity, or the dielectric conduction. These detect the changes in the temperature, physical quantities like temperature, pressure, light sensitivity, macroscopic effects, and other parameters such as the gas detection and light intensity variation. These are done by the conventional sensors, while the quantum sensors use quantum mechanical phenomena such as the superposition, entanglement, and quantization by particle duality to measure physical quantities at atomic and subatomic level. So they manipulate and detect individual quantum systems such as atoms, ions, or photons to achieve unprecedented levels of sensitivity and precision. So conventional sensors have less precise and less sensitive, while the quantum sensors are much sensitive and precise. While the conventional sensors are limited to sensitivity and precision, with their performance constrained by classical noise sources and inherent measurement uncertainties. They are suitable for many everyday applications but may lack the sensitivity required for demanding scientific or industrial tasks. While the quantum sensors have excelled in sensitivity and precision, surpassing the capabilities of normal sensors by orders of magnitude. That is, like even in the small, very, 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 very small change in the environment or the parameter, it is measured by the quantum sensors. They can detect tiny variations in physical quantities such as magnetic fields, electromagnetic waves with extraordinary accuracy, making them invaluable for applications where high precision is critical. But in quantum sensors, the precision, accuracy, sensitivity, and the sensors are very, very capable of detecting applications where high precision is critical. Where these conventional sensors are used, these sensors are used in industries and automotive cars, everywhere in the day-to-day life, in thermostats, pressure sensors, and light sensors and cameras. These are bit easy to purchase and cost effective. These are essential for monitoring and controlling environmental conditions, industrial process, and consumer electronics. while this is opposite for the quantum sensors. It is for specialized application, customized applications, and that demand exceptional sensitivity and precision, such as medical imaging, environmental monitoring, navigation, and scientific research. These enable breakthroughs in fields such as quantum computing, quantum communication, and fundamental physics, where conventional sensors fall short. And these sensors are very costly, and it is designed for customized applications and not for common applications. Where normal sensors are established, established technology manufacturing process. It is commonly manufactured and it is easy for use and easy for manufacturing, such as it is manufactured using silicon, metals, and polymers. They are relatively mature and cost effective with standardized designs and widespread availability. But the quantum sensors are cutting edge technology, drawing on advances in quantum optics, atomic physics, and nanotechnology. They require specialized equipment and expertise for fabrication, operation, and their development often involves interdisciplinary collaborations between physics engineers and material scientists. That is, if we gonna manufacture a quantum sensor, the manufacturing industry setup is very costly, such that the manufactured quantum sensor is very costly, but it has advantages unless it is very precise, sensitive, and customized application view. What are quantum sensors? These quantum sensors encompass a diverse range of devices that depends on quantum phenomena to measure physical quantities with a great precision and sensitivity and even accuracy. And let's see seven different types of quantum sensors and their application, operation, and where it is used and the working principle. And the first sensor is atomic magnetometers. So, how do atomic magnetometers work? It basically works on the above defined principles, that is, quantum entanglement or quantum superposition or interference or wave particle duality. Within these four, it will work, and let's see the working principle. Typically, these atomic magnetometers are made of alkali metals like rubidium or cesium. These devices utilizes the phenomena of quantum spin precision, this which is different from the four phenomena we have discussed further before. Let's say, how do quantum spin precision works? There are different types of phenomena. The one of the phenomena is quantum spin precision, where the spin orientation of atom changes in response to an external magnetic field. So everyone know about the atoms in the particular metal or a material. So in rubidium or cesium, there are atoms in their home position. Let's say when magnetic field is applied, the orientation of the atom changes in response. So with this change, the measurement of atomic or quantum sensors work with this change and it shows some output, even in precise change. How it is operated. So atoms are polarized using optical pumping techniques, aligning their spins with an external magnetic field. So let's say there is a rubidium metal in a small fabricated wafer. When these atoms are polarized using optical pumping techniques, aligning the spins with an external magnetic field. Even when an external magnetic field is applied, it aligns to the magnetic field according to the optical pumping techniques. Subsequently, the precision of atom spins is measured using laser light or radio frequency fields. So when it is spinned using a laser, these are noted, and the changes in magnetic field after the precision frequency falling for the precise measurement of magnetic field variations. When the magnetic field variations are varied with the change in the radio frequency or the laser light. Simultaneously, the precise measurement of magnetic field variations are noted down by the atomic magnetometers. So this is the working principle and the operation of atomic magnetometers. So let's say you have a detector, you have a detector here, and this is the light source. That is the this is the radio frequency or the laser light. Laser light. And this is the pumped laser source. It is pumping in such a way that this is perpendicular to the light source. This is perpendicular to the light source, and the magnetic field is in this direction. The detector finds any interruption or disruption in the input light source. When it is detected, the resonant atomic medium is formed. What are the applications of atomic magnetometer? These are used in magnetocephalography and magnetic resonance imaging, that is MRI. These are generally used in MRI scans and map brain activity and detect abnormalities in the brains or the required MRI scans. And even this is used for geographical exploration, where this is used to explore the quantity of mineral like oil and gas and archaeological surveys to map subsurface geological structures and detect anomalies. So basically, these are even found out using techniques like using lidars or radars or sonars. These are conventional methods. The advanced methods are using atomic magnetometers. And the next sensor is quantum gravimeters. So these the how do quantum gravity meters work? The working principle is very simple. That is using the interference of matter waves, typically cold atoms, to measure gravitational acceleration. So what is gravity? That is in Earth's gravitational field, that is 9.8 meter per second. The quantum gravity meters use the interference of matter waves, typically gold atoms, to measure gravitational acceleration. How it is operated? Uh, like it's a bunch of gold atoms. A set of gold atoms or cloud of gold atoms is released from a trap and allowed to fall freely under gravity. So when it is freely fall under gravity, their matter waves interfere with each other. By precisely measuring the interference pattern, the gravitational acceleration can be determined. So when, let's say, you have a well-defined uh, data set for the gravitational field for a particular atom under 9.8 meter per second. When the gravitational field is varied, the interference patterns changes. So by the precise measurement of difference in the interference pattern, the Earth's gravitational field or any gravitational field measurement is done. Because of the variations in the gravity due to changes in the density or mass distribution can be detected easily using high sensitivity. So to detect the gravitation field or the gravity, these quantum gravimeters are used. So let's say a cooling or trapping, that is, it's a container, it's a vacuum chamber where the atoms are released. So there are around 10 power 6 atoms, and it's freely fall from a certain height for a particular gravity. When it is interferometer acceleration sensitivity, that is inference, the property of quantum mechanics, which is used to detect the change in variation of the gravity, where quantum gravimeters are used. Basically, these sensors are used in Earth's gravitational field to detect subsurface features such as oil and mineral deposits, underground cavities, and water reservoirs. This is this application is even done using atomic magnetometers, and even it is used for volcano monitoring, used to monitor changes in the gravitational acceleration near volcanoes, providing early warning of volcano activity, whether the volcano is erupted, it is predefined, or it is known within a particular defined time, before some particular defined time, so that the people around the volcano can easily escape. So the next sensor is superconducting qubit sensors. What are superconducting qubit sensors? So before knowing about superconducting qubit sensors, we should know what is qubit. Qubit is which is similar to a binary bit, that is 0 or 1. It is the basic unit of information in classical computing or the traditional computing. This is the basic unit of information in quantum computing. That is, bit is similar to computing, where qubit is it's a bit of information which is similar to bit, which is for quantum computing. So let's see what and how is the working principle. So these are artificial atoms made from the quantum superconducting circuits. They exhibit quantum behavior such as energy quantization and coherence. That is, the energy quantization and coherence. These are two of the properties of quantum mechanics. So energy quantization is E is equal to NQ. That is the Neil-Bohr's effect and how it is operated. In a superconducting qubit sensor, the qubit is coupled to an external quantum system, such as the electromagnetic field or a mechanical resonator. You know what is electromagnetic field? It's a EMF, electromagnetic field, or a mechanical resonator is an artificial generation of electromagnetic waves. Changes in the external system induce detectable changes in the qubit's state, which can be read out using microwave or radio frequency techniques. Let's say you have a qubit sensor over here, and the radio frequency signal is detected here, while the qubit state change is seen here, which can be read using a microwave or radio frequency techniques. So superconducting qubit sensors offer high sensitivity as similar to the quantum sensors, other quantum sensors, for detecting electromagnetic fields and other quantum signals. These superconducting qubit sensors are basically used in the field of detecting electromagnetic fields and other quantum signals. So let's see where these applications are used. The applications of quantum computing. These are used in finding the electromagnetic fields and other quantum signals. These are used in quantum computers to perform quantum information processing tasks such as quantum simulation, optimization, and cryptography. You know cryptography, cryptocurrency, which is similar to the cryptography, and which is used in quantum metrology, used for high precision measurements of quantum electromagnetic fields, microwave radiation, and other quantum signals in applications such as quantum metrology and quantum communication. So these are used for communication purposes, where the conventional communication purposes are used using the conventional sensor, that is transmitter, the receiver, and other stuff. where in the advanced quantum computing or quantum metrology, using superconducting qubit sensor, the information is transferred from one place to other place. And let's see the diagram of superconducting qubit sensor. So this is a crystal where the wafer-like structure, the atoms are developed in the wafer-like structure, and it is connected to the defined circuit. So this is the superconductor wire, silicon wire, where the atoms are in a specified distance used for measuring the electromagnetic fields in the circuits. So the next sensor is quantum dot sensors, where these and what is the working principle and the operation of quantum dot sensors. So the working principle is these dots are semiconductor nanoparticles. The nanoparticles are the size of 10 power minus 9 meter with quantum confinement effects. So do anyone know about quantum confinement effects? So what is quantum confinement? Which is the basics of quantum mechanics. That is, it describes electrons in terms of energy levels, potential wells, valence bands, conduction bands, and electron energy band gaps. The quantum confinement effect is observed when the size of the particle is too small, that is, in the atomic level or the subatomic level, to be comparable to the wavelength of the electron. So, where electrons and holes are confined to discrete energy levels. What is the operation of quantum dot sensors? In the quantum dot sensor, the electronic states of the quantum dots are sensitive to external stimuli such as photons. Let's say you have a quantum dot sensor, and when external stimuli such as photons or the light or the electric fields or chemical species fell on the quantum dot sensors, there is a change in the internal structure of the quantum dot sensor. This change occurs with a change in the environment alter the energy levels or charge distribution of the quantum dots, which can be detected using optical or electrical techniques, where the quantum sensor is after sensing the signal conditioning is done. With the signal conditioning, better results are got from the quantum dot sensors. These are detected using optical or electrical techniques. Quantum dot sensors offer high sensitivity for detecting single photons, electric fields, or chemical species. That is, these are used for single photon effects, where quantum dot sensors are used. And the applications are shown in the next slide. So let's say this is the laser pump where the quantum dot sensors are traveling. This is an upconversional crystal for sending only one atom, and with the time gap these atoms or the crystals or the lasers are sent one by one for with a particular time gap. So this is the quantum dot sensor or the detector which is given to a signal conditioning. After signal conditioning, output is displayed. So that with the time gap, one laser is sent to the bottom detector and one is sent to the right side detector, such that to get a better output, sensitivity, and precision. What are the applications of quantum dot sensors? So these sensors, single photon detection. used in quantum optics experiments, quantum cryptography, and quantum information processing to detect and manipulate individual photons with high sensitivity. So, from the above five senses, we can conclude that these quantum sensors are highly precise, accurate, and sensitive to the change in the environment or the detecting agents. And even these are used for biological imaging, used in fluorescence microscopy and bioimaging to label and track biomolecules, cells, and tissues with high specificity and resolution. So it's used in biological imaging and single photon detection. And the last before the cold atom sensors, how these cold atom sensors work and how these are operated. Cold atom sensors are ultra cold atomic gases that is typically under 0 degrees Celsius. Typically cool to temperatures near absolute zero. Absolute zero is something around minus 273 Kelvin to measure physical quantities such as accelerations, rotation, and magnetic fields. So these sensors also work behind the principle of quantum mechanics. What is the operation of cold atom sensors? Let's say you have atoms that are cooled to ultra cold temperatures. These are cooled using the laser cooling or evaporative cooling. So laser cooling is done using the laser atoms with to a particular temperature that is absolute zero or using evaporative techniques. These atoms are then manipulated using laser or magnetic fields to probe the desired physical quantity. So changes in the physical quantity induce detectable changes in the atom's quantum states, which can be measured using techniques such as absorption imaging or atom interferometry. So let's say you have a laser with absolute zero. So when these atoms are passed through the detector, this is the environment where the parameters need to be measured. This is the detector, this is the input device, and with the change in environment parameters, the physical parameters of the atoms are varied or the particular laser are varied. The change in physical quantity, which is the measuring technique such as absorption imaging and atomic interferometry. So this is a typical cold atom sensor or the cold atom sensing device, which is used for atomic interferometry. So this is the imaging lens where this is used to measure the using our eyes. So we use a beam splitter to split the incoming atomic atoms and vacuum port for attracting to the chamber under a test. So here it is cooled and then it is sent to the microfabricated grating to detect it. An alkali metal source is used to detect the change in the physical quantity and it is displayed in the output of the sensor. So the signal conditioning is done here. So what are the applications of this cold atomic sensors? Used in navigation systems for aircraft, submarines, and spacecraft to measure accelerations, rotations, and gravitational forces with high accuracy and stability. So in a aircraft, submarines, and spacecraft to measure the acceleration and the rotations and gravitational forces with high accuracy and stability. What is gravity mapping? This is one of the application for cold atom sensors, high accuracy and stability, used in geophysics and seismology to map variations in gravitational acceleration and study Earth's internal structure. So, to study the Earth's internal structure, these cold atom sensors are used, and even for inertial navigation for spacecraft, submarines, and aircraft, we use cold atom sensors. The sixth sensor is quantum cascade sensors. What is the working principle of quantum cascade sensors? Quantum cascade sensors are semiconductor lasers that emit in the mid to far infrared spectral range. That is in between the quantum mid and far infrared spectral range. How it is operated. In a crucial based sensor, that is the quantum cascade sensor, the laser emits coherent infrared radiation to specific wavelengths corresponding to transitions between quantum states in the semiconductor material. The laser light is directed towards a sample, and the interaction between the light and the sample induces changes in the laser's output. These changes can be detected using techniques such as absorption, spectroscopy, or photo detection. QCL based sensors offer high sensitivity for detecting trace gases, pollutants, biomarkers in the atmosphere and in biological samples. So basically, these quantum cascade sensors are used as gas detection sensors. That is, that is for detecting trace gases, pollutants, and biomarkers in the atmosphere, which is similar to the MQ6 gas sensor in the Arduino and or other gas sensors for detecting LPG or tobacco or it's drunk. For sensing these gases, these quantum cascade sensors are used. So, how these quantum cascade sensors work? Let's say there is a modulator for the current source for the sensor, that is input VCC for the sensor, and there is a temperature control for the quantum cascade laser to send only a particular temperature atoms or the environment. This is a detector or Vigo for the particular setup. When the gas atoms are hit by the quantum cascade atoms, there is deviation from the horizontal axis, that is x-axis, and these are observed in the Vigo. So this difference between the x-axis and the y-axis is determined using the data acquisition, and this data acquisition sends the output of the sensor. So when there is no deviation, its value is 0. While there is some deviation, it is proportional to the amount of intensity of the gas. So for monitoring the pressure of the gas, we have a pressure monitor and a mass flow monitor, and even at a particular temperature, the gas is monitored or controlled or measured. So where these quantum cascade sensors are used. So where these quantum cascade sensors are used. These are used in environmental monitoring, used for remote sensing of atmospheric gases in a particular area. What is the AQI index? What is the pollution level of the environment and atmospheric gases and greenhouse gases, such as air quality monitoring, climate research, and industrial emissions control. So let's say there is a process industry or a cement manufacturing industry. These sensors are used to determine how much amount of pollution or the greenhouse gases are emitted from the industry for the certain radius. So these are even used in the medical diagnostics, such as the breath analysis. So let's say if there is any breathing trouble from a human, this breath analysis is done by using these quantum cascade sensors and blood glucose monitoring, spectroscopic imaging for early detection and diagnostic of diseases such as cancer and diabetes. So easy detection of cancer and diabetes are done using quantum cascade sensors. Next one is the quantum Hall effect sensors. What is the working principle and operation of quantum Hall effect sensors? So how does a quantum Hall effect work? Let's say you have a wafer or a dielectric medium where the magnetic force and the negative charge carriers magnetic field is one side. On the other side, there is a external magnetic field. With the intensity increase in the intensity of the magnetic field, the atoms go perpendicular, or the magnetic field go perpendicular to the conventional flow of the current. This is the conventional method, while the quantum Hall effect sensors use the quantum Hall effect, which occurs in two-dimensional electron systems subjected to strong magnetic fields and low temperatures. It works in the low temperatures and it works in the two-dimensional axis. What is the operation of the quantum Hall effect sensors? The sensor is subjected to a strong magnetic field perpendicular to the two-dimensional electron system. Quantum Hall effect sensors measures changes in the Hall resistance with exceptional precision, allowing for the accurate determination of quantum magnetic field strength. Small variations in the magnetic field induce detectable changes in the Hall resistance, providing high sensitivity for magnetic field measurements. Let's say you have a strong magnetic field traveling in the circuit, which is in this direction, x-axis, and you bring a magnetic field which is perpendicular to it. So the this in y direction, which is perpendicular. So the output changes that is along the z-axis. This is measured, and this physical parameter, change in physical parameter is measured using the Hall resistance, providing the high sensitivity for magnetic field measurements. So how does a quantum Hall effect sensor work? This is the source VCC for the sensor, and when the electric force from charge buildup, it is in the x-axis, while the magnetic force and negative charge is in the negative x-axis, and the magnetic field is along the y-axis. So when an external magnetic field is brought inside the sensor or it is kept near the sensor, the direction of the magnetic field changes along the z-axis. So it is measured along the z-axis. We get the precise measurement for the Hall effect sensor. Hall effect, it works on the principle of Hall effect resistance, which is similar to the conventional sensor. The next, metrology, used as primary standards for resistance metrology and for defining the unit of electrical resistance in the International System of Units. Electrical resistance is ohm, as we all know, that is defined in the SI Standard International System of Units. Semiconductor characterization, used for precise measurements of electron mobility and carrier concentration in semiconductor materials and devices. So these sensors are very precise and which is sensitive to the change in the environmental parameters. And the final sensor is nitrogen vacancy sensor. The nitrogen vacancy centers are defects in diamond crystals that possess quantum properties such as spin-dependent fluorescence and sensitivity to magnetic fields. How it is operated? Can anyone know the nitrogen vacancy, how it is operated and the working principle? Okay, let me explain. These nitrogen vacancy centers are created by introducing nitrogen and vacancies, missing carbon atoms, into a diamond crystal lattice. Nitrogen vacancy center possesses electron spins that can be manipulated using external magnetic fields and microwave radiation, which is similar to the quantum cascade sensor. The spin states of nitrogen vacancy centers are sensitive to changes in the surrounding magnetic field, allowing for magnetic field sensing. Changes in the spin state of nitrogen vacancy centers include detectable changes in their fluorescent properties. These changes can be measured using techniques such as confocal microscopy, where the fluorescence intensity or polarization is recorded. So, with the change in the microscopy of the fluorescence intensity, with the change in the input and the output, the polarization is recorded, and the precise measurement of the sensor is the working principle. So, let's say these are used for magnetic sensing, used for magnetic field measurements with nanoscale resolution in applications such as magnetic resonance imaging, magnetic microscopy, and magnetic resonance. Post microscopy, biological sense, used for detecting biomagnetic fields, studying molecular interactions, and imaging biological samples with high sensitivity and spatial resolution. Quantum metrology is the field of science concerned with the precise measurement of physical quantities using quantum techniques. So, how quantum metrology is? It's a field of science concerned with the precise measurement of physical quantities using quantum techniques. This is done using quantum cascade sensors or the quantum Hall effect sensors, such as squeezed states and quantum enhanced measurements enable measurements beyond the classical limits imposed by noise and uncertainty. What is quantum metrology holds promise for applications in precise measurement, sensitivity, and accuracy, and it is also used in navigation and fundamental physics research. So, we are going to end this lecture by seeing the last topic for the applications of quantum sensors. So, where these quantum sensors are used and across various fields, these are used. One of the field is quantum magnetometry for geological exploration and medical imaging. And the next field is quantum gravimetry for oil and mineral exploration and underground mapping. The last field is for navigation and inertial sensing in aerospace and defense. Quantum communication and cryptography for secure data transmission. These quantum sensors are revolutionizing industries and enabling transformative advances in science and technology. So these are the four applications of quantum sensors. So at the last but not the least, the challenges in quantum sensors. So these are not cost effective, these are very costly, and the scalability of these sensors are very difficult. It's not for mass production. Mass production cannot be done. Technical hurdles such as decoherence and environmental noise and limit sensor performance. So it can be used in a particular environment according to the sensor's parameters. So it even offers unparalleled sensitivity and precision. They also face several changes. So these are interdisciplinary collaboration and investment are needed to overcome these challenges and realize the full potential of quantum sensing. So these are the challenges in quantum sensing. So here we are end of this lecture. In this lecture, we have learned about what is quantum, what are quantum sensors, working principle, operation of the seven quantum sensors, and the differences between the conventional sensor and the quantum sensor, and the applications of quantum sensor, quantum metrology, and the challenges in the quantum sensors. Yeah, thank you for this listening the wonderful lecture.